All right, here we are entering course review lesson number 9, rotational motion. We're going to go over kinematics, rotational kinematics, and some things about rotational inertia, torque, and how they all tie together. All right, let's begin. Just remember that for linear, first it's the variables, right? Being clear that there's a very clear connection between linear motion variables and rotational motion variables. So remember that we have our position, we have velocity, we have acceleration, we have mass, we have force, and are there any others? I think that might be up. So this is linear, of course. So for rotation, the angle is considered the position. So we end up having delta x's as well, and we have delta thetas as well. It's a change in a rotation angle. If something goes from one position to another position, we'd call that delta theta. We have omega, which means for rotational speed compared to linear speed, we have possible delta v quantities as well as delta omega, which would represent a change in its rotational speed. We have acceleration being replaced with alpha. That's angular acceleration, rotational acceleration. It's the rate at which this changes with time. And omega is the rate at which theta changes with time. A is the rate at which v changes with time, right? A equals delta v over delta t. And v is the rate at which your position changes with time, right? V equals delta x over delta t. It's all the same, right? Alpha is the rate at which omega changes with time. And omega is the rate at which the angle as it rotates changes with time, right? For mass, we have, which is an inertia thing. Remember that mass is inertia. More mass is harder to change its motion. Less mass is easier to change its motion with a net force. So the equivalent in rotation is rotational inertia, also known as sometimes the moment of inertia. And then for force, we end up with torque, right? Remembering that torque is a product of the perpendicular force and the radius from the center or axis of rotation. Simplest visual example is, a pulley that has a force being applied like this. R goes from here to here. This F is perpendicular to R, so we don't have to worry about any sines or cosines or any trigonometry stuff to figure out the F perpendicular. And if that's true, if it's these simple cases, it's just whatever that force is times R. Remembering that technically it's the definition is F, usually in a textbook, F sine theta times R, recognizing that F perpendicular is F sine theta. So if there was a case where, here's R and then there's a force like this F being applied, then, and this is the angle they show theta, be careful about where that angle is, like I've told you, then this component of this is the force that's being applied, this is F perpendicular, right? This is opposite to that theta, and therefore it goes with sine theta, and that's why F perpendicular is equal to magnitude of F sine theta, right? So if you have angled problems like this with the force is at an angle, then you can't forget that there's some component of that force that's perpendicular to R, and that's the only piece that gets torque. Parts that are parallel, like this piece here, which is F parallel, gets no torque. It's actually just pulling straight out. Again, if this was imagined as a rope pulling straight out, we know that rope pulling straight out like this wouldn't make it turn. But this one right here would make it turn. It would make it rotate this direction because it would get some torque, right? So that's that part. All of the kinematic equations, remember, can be rewritten for rotation, although I'm not going to do that just yet. Just remember there's also a connection with all of the graphs. So if we were to look at, x versus t graph, which is, let's say, linear, which we would say that's constant speed motion, because we know that the slope is the velocity, that constant speed velocity, then if in a similar way they give you a theta versus t graph, again, which references some rotational angle that it's gone through, theta as it goes from one point to another point, and t would be how many seconds it takes to go from here to here, and they happen to show that it's like the other one above it, then this is constant rotational speed. Because theta is the rotation, the like position, right? This is like maybe if this was 0 degrees and this is, I don't know, a third of 2 pi, then it would be 2/3 pi. I don't know, it looks like roughly 2/3, although not really sure, but you get the idea. So if it's linear like that, then that's still, our interpretation is the same. It's constant speed. This slope is omega. And since the slope is constant, then omega is constant. That would be true as long as the net torque is 0, just like up here. This would only be a true graph for the linear case if the net force is 0. If the net force is 0, there's no acceleration. And if there's no acceleration, then the speed is constant. And that's why the slope of this is constant here. It's not a changing slope. Same thing down here on below. If something's rotating, but there's no net torque, meaning there's multiple torques that are canceling, or there's just no torques. It's just something in outer space just rotating. In both cases, the net torque is 0. We'd say the angular acceleration is 0, which means omega does not change. Omega is constant. Just like up here, we would say v is constant if it's not accelerating, right? That slope, when we say slope is omega, it's this right here. This is the slope, right? So when we think of rise over run, right? Think of this piece as rise, and delta t is like run. So you're doing a rise over run for a theta versus time graph. You can take 2 points anywhere you want. The difference here is delta theta. That's the part that's in the numerator of this one over here. And the sideways distance is delta t, run, I guess, right? Delta t is like a run, rise over run. So when you see things like this here in this format, this is like our y, right? This is like our x, and this is like our m in math class when we see y equals mx plus b, right? In math class, this would say m equals delta y over delta x, rise over run, right? So when you see the delta over delta, that's an immediate indication. That's a slope. Slope of what type of graph? Whatever's here it goes on the y-axis, and whatever's here goes on the x-axis. That's that. Then there's the possibility that they're not linear. These graphs certainly may not be linear. If there's some sort of acceleration occurring rotationally, just like in the linear case, if the horizontal position versus time graph has some sort of curve to it, then that tells us the net force is not equal to 0. There is some unbalanced amount of force. Reminding you, how would we get that? Well, we would, sorry, take that away. You would have to think about the forces, to the right, to the left, or up and down, figure out what the net force is. And if it's a horizontally accelerating object, then there must be more force to the right, if that's the way it's moving, than there is to the left. And F net would be the difference between them. Reminding you again that that even in a curved graph, V is the slope of that tangent line, right? V is the slope of that graph. So in the rotational case, if you get a theta versus time graph that looks like this, our interpretation is the same. This thing's not only rotating, but it's gaining rotational speed faster and faster and faster as it rotates. What would this slope of this line here represent at this instantaneous mark of maybe 2 seconds? The slope here is omega. It's called the instantaneous rotational speed at the 2-second mark. If we drew a tangent line at some other moment of time, then the slope wouldn't be the same. Before 2 seconds, the tangent line would have been less steep. After 2 seconds, like over here, again, the slope would be more steep. That's because it's going faster at that point. So you need to know that. And you also, lastly, need to know oh, I didn't make that complete. That over here, this means when this graph is being shown, when there's some sort of curve to it, like I said, that means the net torque is not zero, right? There is some amount of unbalanced amount of torque. And that means there that the angular acceleration is not equal to zero, meaning it is accelerating, not equal to zero in the top two. It's not a zero acceleration. It is accelerating, right? So there's that part. Then there's the part where they might, ask you to show a graph. Well, if it's let's say it's A versus T. In fact, no, going back up. Then maybe let's look at the V versus T graphs, right? V versus T for something that's accelerating would look like this for constant acceleration. This one would be constant speed. This horizontal one means it's a constant value, right? If it's linearly increasing, that means the velocity is increasing at a constant rate, right? Remember, you can take any 2 points here and say this is delta V, this is delta T, and A is delta V over delta T, right? It's a slope. Same idea. Now we're looking at this one. V is delta X over delta T. A delta over delta is a slope. A slope of what graph? Sorry, make sure we're the wrong one. We're looking at, not that one. We're looking at this one here. A equals delta V over delta T. So we're looking at a velocity versus time graph, which we are, velocity versus time graph. And A would be the slope, right? Slope of that linearly increasing graph is the acceleration. This horizontal line was just to remind you that if you see a graph, a V versus T graph that's horizontal, that means it's constant speed, zero acceleration. So we should be able to say the same thing for rotation. If we see an omega versus T graph that is actually, again, looking like this, then that tells us this thing's rotational speed, which that's what omega is increasing. This is increasing, right? These values are increasing. And so that tells us it's accelerating. So alpha is the slope. Just like above, A is the slope of a V versus time graph. Well, alpha must be the slope of the omega versus time graph, which brings us to this one. Alpha is the slope of the omega versus time graph, right? So there's that idea. Then lastly, if we went over to our acceleration versus time graphs, which usually they're constant. Most of this year is about constant accelerations. If that were true, then it would be constant. Whatever the accelerate, if it was 5 meters per second squared, then this would be the 5 mark. It would show, sometimes they draw them nice like this. Other times, as you've seen, they show like kind of scattered data points. You got to think about, all right, it's kind of like a flat line with some error that might be in the instrument that's making the measurements. So for our scenario, if there's a constant acceleration, before I talk about rotation, if the acceleration is constant, that means the net force is constant. Because F and A mirror each other in that sense. They're not the same value, but right, F equals ma, right? So if this value is constant, then this value is constant. A is constant, right? And that's where why most of the problems involve constant acceleration, because they gave you scenarios where there were certain forces, but those forces didn't change as the motion began. Those forces stayed the same. So we can say the same thing now down here. If they show us an alpha versus time graph and they say that the torque is constant, the net torque is constant. As it rotates, there's something that continually applies a torque, but that amount of torque doesn't change. Then the angular acceleration will be constant, because that's now Newton's second law is like our F equals ma, right? This is like F net equals ma, right? So if the net torque is constant, then the angular acceleration is constant. And that would look like what on a graph? Like this. Maybe this is the number 5 radians per second squared. That's a rad, radians per second squared. all of the areas still have the same meaning, right? They all have the same meaning, so you can't lose track of that. We're talking about areas under the graphs, and there are definitely going to be questions that have to think about areas under the graph. They all still have the same meaning. The area of an x versus t graph has no meaning. The area of a v versus t graph does. This area now represents the displacement in that amount of time up to this point. And again, they'll give you values along both axes so you can figure out what the area is. That area does represent the linear displacement. For omega versus t, if it was the same thing, this area represents the change in the angle. If it was a circle again, that there's some rotational angle it's gone through, which would be like delta theta. Then delta theta, that rotational angle that it goes through, is actually equal to the area of this graph here, at least underneath the function, and we say bound by the x-axis, meaning it doesn't go below the x-axis, and then it's bound by whatever the moment in time is where they're having you check to. If they say up to 5 seconds, then your triangle would stop at the 5-second mark, right? And also for the also for the linear acceleration graphs, those have meaning. If it looked like this, then this represents the change in velocity in that amount of time. And again, they'll have numbers here, so you can figure out what that is. So if we're looking now at an alpha versus time graph, and it looks similar about a rotation problem, this represents the change in not v, but omega in that amount of time. Right? Assuming that they're showing some sort of constant acceleration graph. All right. Last part of this, I would say, is the kinematics. Just be aware that, again, they're all on the equation sheet. They're all on the equation sheet. Why is it saying no to me? I'm not sure why it's saying no to me. They're all on the equation sheet. So if you saw, x of t equals x initial plus v initial t plus 1/2 at squared, then that just gets replaced with theta. X's replacement is theta. V's replacement is omega. A's replacement is alpha. And you get to use the same formula and the same format for the rotational problems. If you're looking at v final equals v initial plus at, which, by the way, up here, it doesn't matter if we write x of t or someone just writes x final equals. Also worth knowing that you could write this one as just delta x equals v initial t plus 1/2 at squared. Meaning if instead of writing x of t originally, I had this written as x final, and I now subtract x initial from both sides, now I'm left with x final minus x initial. That can be written as delta x, the displacement. So no matter where it started becomes arbitrary. We just know that when time started, t was equal to 0 seconds, it moved some displacement from there, delta x, in that amount of time, assuming that you know the acceleration. So pointing out, you could have written the one underneath it the same way. Delta theta equals omega initial t plus 1/2 alpha t squared. That's sometimes more useful. The other form of this position formula really only becomes more useful if the x initial here is some number that they have to use. Oh, the runner started at the 10-meter mark, and now we got to model his motion after that part. Then you wouldn't want to represent it as delta x. You'd want to leave it in that original format, and x initial would be the number 10. But if all that matters is the displacement that is achieved after the motion begins, then this format above is really the best way to go. Here's our kinematic equation number 2. It's a way of finding out what the final velocity is of something after it's accelerated for a certain amount of time. Same idea, rotation. This is a formula that gives us the final rotational speed, assuming that it started with some initial omega. Could be 0. In a lot of cases it is. You cross these out, but not always. And it gives us a way of, again, calculating the final rotational speed, knowing that it's been rotationally accelerating for some amount of time. Right? And then very last kinematic is this one, where this is the one that doesn't have time in it, and it's giving you a way of normally determining a final velocity of something after it's moved through some distance, not after accelerating for some amount of time, like this middle formula does. And so this formula would be just replacements again, delta theta. Right. So those are the kinematics. Now we're going to talk about torque a little more, relatively briefly, as I did already. But again, to get torque, you have to have some perpendicular force to R. And if this was again, the rotational axis that goes right through here, R always goes from the center out to the end of wherever the force is being applied. If this was a rope, by the way, especially if it's a, well, I'll just say if it's a rope applied, it's attached here. So it's applying the force at that position. Again, torque is, in general, it's the magnitude of the applied force. So I won't label this as necessarily F perpendicular. I'll just say it's F, whatever the magnitude of the applied force is, sine theta times the lever arm distance. The lever arm distance goes from the middle out to where it's being applied. That gives you the leverage factor. So R would go here, right? But remember that this theta is the angle between the force vector and R vector. These are two vectors. And in this case, if R is thought of as a vector going from here to here, and F is a vector going from here to here, then the angle between them is 90 degrees. And when we do sine of 90 is 1, right? And that reduces down to just F perpendicular times R. But remember that if the problem instead involves some sort of angled force, like this, then I always draw a dotted line to extend R all the way out. And then it helps me draw in the F perpendicular and the F parallel, because F parallel has to be parallel to R. Right? And there's your angle theta. And now if this was the rope pulling in this direction, we'd have to really use that sine function, say F perpendicular is now F sine theta, because that component is opposite to theta. Right? And then if we insert that into the torque formula, which is F perpendicular times R, we just stick this expression in for F perpendicular, we get F sine theta as representing, again, the perpendicular force, this amount right here, times R. Yep. All right. Next, if you get those problems where, you have something that's balancing like this, and there's some object over here, and there's another object, let's say, over here. In fact, I'm going to change that. These can be in balance even if they're not the same mass, right? That if there's, think of these as positions here. If there's a little m over here, and then there's a big M over here, and let's just say this was 10 kilograms and this was 5 kilograms, then those torques are created by their weight. mg is down, right? R goes from the center out to there. So the torque on this side, which is in that direction, would be 2 units of distance. This is like 1 unit of distance, 2 units of distance, right? So I can just say, just conceptually, you can do it this way and just think it's 2 units of distance. Remember, torque is force times distance. So you can just think, all right, the distance is 2 units of distance. I reversed the order a little bit, but it doesn't matter. It's multiplication. Times, let's just say it's 1 unit of weight, 5 kilograms. So this guy is going to get how many units of torque? 2 units of torque. How about this guy? This guy has twice as much weight, because 10 kilograms here is twice as much as 5 kilograms, right? So how much torque does he get? If we're thinking of, again, distance first, this is only, I'm calling this section 1 unit of distance. So he's only has 1 unit of distance times how many units of force? His weight is the force, twice as much. This is twice as much as 5, but 2 here. What is his torque units? 2. What is the other guy's torque units? 2. These will be balanced, right? If, of course, we were to move this guy slightly to the right, then he'd have more torque than the other one. And at that moment, since the D is now not one unit anymore, but maybe 1.1, the torque over here would come out as 1.1 times 2, which is 2.2. That's more torque in this direction than the 2 units we have over this way. So it becomes unbalanced at that point, and the net torque is in this direction, which makes sense because we know it would then it would tilt down, right? Next is the beam problems. You have to remember that if you get these problems, and you probably will, that the center of mass of the beam is in the center. This is the beam, then we imagine that there's some center of mass of the beam, which is here, which is the mass pulling down is Earth's gravity, mass of the beam, up at B for beam, times, and we usually refer to this as L. So this would be times, mass of the beam times G is what I would say. Erase that bottom part. And now we see that this is a rope above again. This is a rope up here, rope, pulling in this direction, right? This is now a tension force, which means that there's components. There's this component here, and this component that I just drew is perpendicular to R. Right here, this is F perpendicular, because F perpendicular is pointing this way. And which way does R go? R goes from over here at the side all the way up to here. So those are perpendicular. So the way we would have to do that is, be careful with these again. If this was the rope again, and the amount of force is pulling it in this direction, and R goes out like this, and now you know that this is the F perpendicular amount, then that theta, you have to look at which angle they give you. Sometimes they give you one angle, other times they give you the other angle. If we're going to use a sine function to represent F perpendicular, the angle has to be here, in which case F perpendicular from the rope would be equal to F sine theta. Yeah, come back later. I'm in the middle of a recording. Yep, thanks. All right. So the perpendicular force from the rope's tension would be up like this. And so the amount of torque that gets, the torque by the rope, is equal to the amount of perpendicular force from the rope times how far it is being applied from all the way over here, which is all the way over here. That's times L. Right? That would be F sine theta times L. That's how we would model that. How would we model the torque being generated by the weight of the beam itself? Again, we imagine collapsing all of its weight into the center of mass, which is here. R then goes from here to here. Noticing that R is L divided by 2 because it's half of the length of the beam. So when we say the torque due to the beam's weight, it would be F perpendicular times R in general. What is F perpendicular? It's L divided by 2. I'm sorry. What is F perpendicular? It's weight, which is definitely perpendicular to R. So we put mass of the beam times G. And then R would be re-expressed as L over 2. And if this, like in a lot of their problems, is in equilibrium and they say, hey, this thing is not moving, then recognize that the torque due to Earth's gravity, this one right here in the middle, is trying to get this beam to rotate down. That's what Earth's gravity's trying to do. The rope, on the other hand, which has a component upwards like this, is trying to make it rotate this way. And those torques would have to be equal. So make them equal curves and make them think that these are equal, right? So if those torques are equal, you would set this equal to this to model that. Torque from rope equals torque from the beam's weight, right? And, could you solve for the tension in the rope? Yep, if you had to, or derive a formula for it, set them equal and solve for F. If they decide to throw a man on here, and they do, remember that the man now also, his weight generates some extra torque in the downward direction. So if there was the original problem I just described with your rope like this, but now there's a man sitting in the middle, standing in the middle, then now his center of mass is pulling down with the mass of the man plus, times g, which is his weight. And his position could be anywhere on here, but usually they make it either 25% of the beam's length, which is like here. Sometimes the man's at this position. Then that R would be L divided by 4. Or they put him over here, in which case R goes from here to where the guy is. That would be a distance of 3/4 L, right? Or those are the three positions they put. So you'd have to think about him again and his placement, right? So the torque due to the man would be F perpendicular times R. F perpendicular is just his weight, mass of the man times G, where R depends on where he is, right? If he was right in the middle, like originally said, then R would be L divided by 2. Which team is he on? It's all gravity. They're the same team. The beam's torque and the man's torque is due to Earth's gravity. They're all trying to pull down. So this term for the torque due to the man's weight would have to be added to which one of these? It would have to be added to this one. And therefore, the total torque in the downward direction would be this expression plus this expression. And if they say it's not moving, that total downward torque due to the beam's weight and the man's weight would have to be equal to this expression for the torque created by, because this is the only thing that's keeping that thing up, the torque created by F perpendicular in the rope. All right, that's enough about torque. I am going to then just remind you that Newton's second law. Actually, I'm not going to do it in Newton's second law. Now we're going to talk quickly about rotational inertia. For point masses, it's mr squared. So reminding you that if you get these problems where something can spin like this was the first problem you did. This is the axis of rotation. And they have some balls, and they say this whole thing's going to get spun around. And you needed to determine the rotational inertia of the system. It's the I of the one piece plus the I of the second piece plus the rotational inertia of the third piece plus the rotational inertia of the fourth piece. And this represents the rotational inertia of the whole system. How do you figure out any one piece's individual contribution to the difficulty you experience when trying to rotate it? This guy's individual rotational inertia. You apply this. So for him, this guy, if he was number 1, he was number 2, he's number 3, and he's number 4, you'd say it's his mass times R, assuming it's going to be spun around the middle. That's just they would label that as R, more than likely. R squared, R1 squared. What would this guy's be? I4 would be his mass times his distance from the middle out, which is R squared. Right? And you would do that for all of them. And you have to represent the rotational inertia of the system. You add them all up. That's how you do point mass. That's again, using point mass approximations for rotational inertia. On the other hand, of course, you do get some particular geometrical shapes, like the disk, which I think is 1/2 mr squared. Again, you don't have to memorize that. They would give that to you in the problem. You have the sphere, which I believe is I don't even remember if it's mr squared. It might be mr squared. I don't remember, to be honest. I remember that the hoop, I think, was hoop has the most so the hoop, which looks like this. I for the hoop, which has the most rotational inertia, I think is 4/5. Don't hold me to it. It's not something I ever wanted to memorize. This is the mass of the hoop times the radius of the hoop. I think this one is, again, the coefficient is 1, I think, not 100%. And I think this coefficient is 1/2. Again, I haven't memorized it. It wasn't useful for me ever to do that. But they're different coefficients. Just know that you don't have to memorize them. But definitely know that the one that has the most rotational inertia is this hoop, because all of its mass is spread out along the sides. The one that has the least rotational inertia is the sphere. It has more evenly distributed, and lots of it are distributed around the center. Where for a disk, yes, it has some mass in the center, but it's all along one plane, where the sphere distributes that in the center in all 360-degree direction. So this guy has, again, the largest. his rotational inertia is the largest. This has the smallest. That means they're not, if it's the smallest rotational inertia, it's easy to get rotating. And this one is in between. That's why if they race them down a ramp, remember the one that can get rotating most quickly, which is this one, is the winner. The one that gets rotating more slowly, which is the hoop, is the loser. This guy comes in second. Remember that if they give you a problem, which they do usually each year, and usually it's a merry-go-round, and they show a person standing here at a distance r, and you have to now represent the rotational inertia of this system. This is a disk. You should know that this is a solid disk just turned sideways. It's like a pulley. A pulley is a disk too. They both, the pulley and this all are represented rotationally for their inertia as the disk. So if someone said, what is the system's rotational inertia? It's the rotational inertia of the disk if the man wasn't on it, plus the rotational inertia of the man using the point mass approximation that his center of mass is now a point mass, right? Which means for the man, it would be the mr squared, like we talked about. But we're not really doing a sum, it's just one man. So I would put man's mass times his distance. You know, if that was, careful, if that was where I put it, and the real radius of the disk is r, then and he's at r over 2, then you'd have to put r over 2 there, and that whole thing would have to get squared, right? What would the rotational inertia of the disk be? I believe it's 1/2 mass of the disk times the radius of the disk. Radius of the disk, again, is the radius of the disk squared, and you'd have to add those together. So the total rotational inertia of the system is the disk's rotational inertia plus the man's. No different than saying, what's the rotational inertia, or what's the linear inertia of a car? It's the inertia of me, which is my mass, plus the inertia of Caleb, which is his mass, plus the mass of the car. That's all inertia. And what's the total inertia or total mass? It's the sum of all the masses. The same idea. We're just adding up all of the inertias. Be aware of that. Also be aware, but I don't want to repeat myself, but you know, angular momentum is conserved. When this guy walks out or in, the rotational speed omega will change. When he walks outward, the rotational inertia increases and omega decreases. If he walks inwards, then the rotational inertia is getting less because systems bringing some of its mass closer to the center. I is going down, omega is going up. When that happens, although their rotational speeds change, L, the angular momentum, does not change. Again, the forces are all internal. And if all the forces you're looking at are internal to the system, then the overall momentum of the system cannot change. Certain parts of its momentum can change, like M and V for linear. M and V might change, but in a way that if M goes up, V goes down exactly in proportion, so the product MV stays the same. Those are all conservation of momentum ideas. Conservation of momentum means the total doesn't change, right? And then one of the last things I will say, probably, I think, is the torque. The idea that you can, he has a second law for 3 things: circular motion, for linear motion, for rotational motion. This is like our F net equals ma, right? You replace them as such. When we say that the acceleration for in the linear case is proportional to the net force, but inversely proportional to the mass, we can say the same thing over here. The angular acceleration is proportional to the net torque and inversely proportional to the rotational inertia, because these are all the same, these matches. Like that, right? So more rotational inertia, for whatever the reason, the rotational acceleration will decrease. Remove, some parts from something that's going to spin, then technically it has less rotational inertia. So if you try to spin it the next time, alpha should be a little faster because you just removed some pieces. M has decreased, I should go down, right? Also pointing out, if we were to graph these, what would an angular acceleration versus torque look like if they say that the torque is constant? If the torque is constant, then what would the angular acceleration be? If this is constant, then this is constant. What would this graph look like? It would look like that. On the other hand, what if they decided to say that over a few trials of an experiment, they kept increasing the rotational inertia of something that was rotating? They applied this, let's just say, the same force, and it got the same torque in all of these experimental trials. So some wheel, again, applying the same force, getting the same torque every time. But we keep just adding we keep adding blobs of clay to it or something, so that the rotational inertia each trial is going up. What would this graph look like? Alpha versus I then. Would alpha increase each time you added something, or would alpha decrease? It would have to be a decreasing, right? More inertia, less rate of change for omega, which is called alpha. You're not sure what the graph looks like? Just come back to it, right? It's right here. Those two variables are inversely proportional. Alpha and I, inversely proportional graph looks like this. All inversely proportional graphs look like that. What would the orbital velocity of a planet look like versus r? It's inversely proportional. It's actually, I believe, inversely proportional to the square root of r, but it's still the same sort of curve. In this case, you'd say alpha is inversely proportional to I. So if you do a bunch of experiments where I keeps increasing, no matter what those values were, each data point should fall along this curve. You know, when you have a computer fit it, it would complete the curve like that. Also, pointing out that, I think this is the last comment, if they did the opposite, which is said, you know, here's a thing that can spin, let's say, this thing is a little turntable and it's allowed to spin, sitting on a table. And we hang weights from it like this, and we hang weights from it like this. And this thing will also spin, right? It's just a pole that goes through another pole. These are weights. Well, there's some rotational inertia here, right? Because, well, it has some mass and some weight, and they have distances from the axis of rotation. The axis of rotation would go straight down that. If they described an experiment where, you know, there's a little rope here, for example, that pulls to get this thing rotating, and that each time the torque gets a little larger. We do it in one experiment with some amount of torque 1, and we determined the angular acceleration alpha 1 experimentally. Then in another experiment, we increase the torque, we pull a little harder, and then we see the angular acceleration has increased yet again to a new acceleration alpha 2. Gains rotational speed more quickly. We do it a third time, we do it a fourth time. And they now say, now we plot out our data for the net torque that we created in all those trials versus the angular accelerations we computed or determined. What would this graph look like? Always come back to Newton's second law. Right? These are proportional to each other, regardless of how you go through that experiment. If you're collecting torque versus angular acceleration data by changing the torque each time and then determining what the new angular acceleration is, if these are proportional, these should come out linear in some fashion. What the slope is, but what would the slope represent? This is on our y-axis again. This is on our x-axis. Right, so this is like x. Anyway, this is like our x-axis, right? Alpha is on the x-axis. It's confusing. So this is our angular acceleration axis, which is on the, angular acceleration quantity, which is on the x-axis. So it's like this. This is in a form of y equals mx plus b, right? Y goes with that. X goes on that axis. Then what is the slope? Well, if this was y, this was on x-axis, the slope is the rotational inertia. So I is the rotational inertia. I'm sorry, I didn't mean to say that. It's true that I is rotational inertia. I is the slope of this graph. I is the slope of this graph. So if you had to do an experimental problem and they gave you the data set and you plotted it out, torque versus angular acceleration, they say now use your rulers to draw the line of best fit. Sure enough, you're in the test drawing a line like this with your ruler. Now determine the rotational inertia of the system after you looked at their data table that they gave you and a blank graph and you plotted it all out, because they do that to you sometimes. And you now see, oh, there it is, it's linear. Now let's draw a line of best fit. And again, it might be a little scattered. They usually add a little error like this. You would then still just try to draw the best line of best fit straight down the middle. Now, if you're getting the slope from this, it's the slope of that line of best fit. It's the slope of whatever you've drawn. And what would the slope represent? The rotational inertia. And sometimes they'll say that. That's the final thing you're doing. Find the slope and tell us what the rotational inertia of this whole system is from that data using this method. The slope of the graph after you plot out torque versus alpha. All right, I think I'm pretty much out of time. do have a couple more minutes. I just have to think to myself. That was my, in a nutshell, rotation. Went through the kinematics. I went through rotational kinematics. I went through torque, some of the common examples. Went through Newton's second law. Went through the rotational inertia ideas. All very brief, but it's a summary. I didn't talk that much about angular momentum, but I did in the last unit. So I didn't talk that much about it. And I guess, as I think to myself, that would conclude this lesson. All right, this was an optional assignment, as you guys were all told before it was posted. So if you did watch it, good for you. Nice job. Proud of you again. All your extra work, even last minute extra work before a big exam always helps. So, nice job. All right. I might very well make a simple harmonic motion. It's the last thing that I haven't reviewed. I might very well make one as another optional video, but I can't make any promises. If not, that simple harmonic motion stuff was very recent. That was just in the last few weeks. So hopefully it wouldn't be that big of a loss for you guys. But all of the stuff prior to that, I can say I've now covered. All right, guys. Nice job. Nice job. You'll do well. Be confident. Go right into that test and knock it out of the park. Whatever you get, as long as you know you tried your best, be happy with it and be proud of it. I certainly will. Be proud of you. Nice job.